Okay, there we go. Hi, everybody. Today I'm going to be talking about an R package I've been developing recently. It's called ChIP-tsne, and it's basically an application of tsne in ChIP-seq analysis. So it might seem like a strange thing to do to apply tsne to ChIP-seq, and really what got me started thinking about this was 4 years ago at a different ISCB conference. I saw this image for the first time. And this is a tsne projection of images of faces. There's about 40 individuals in here, 10 faces per individual, and the dimensionality of this is just the grayscale pixel values of these images. And tsne is able to separate all the individuals really well, and then in this detail, you can see that this individual's face is split based on their expression. So this is a really kind of subtle distinction for tsne to make. And so to skip ahead a little bit, this is what happens when you apply this to ChIP-seq data. So this is a tsne projection of, there's actually two replicates for two conditions. The purple and the green are the two conditions, and they agree with each other very well. There's the main kind of thing going on in this tsne space is high enrichment on this side, low enrichment on this side, but you can see these subtle differences in peak shape here. There's double peaks and things like that. But then you also see differences between the two conditions where here green is higher and there's a little space here where the purple is higher. So let's back up a minute and just kind of introduce the bits that are going into this. So tsne is a dimensionality reduction technique. PCA would be another example. UMAP is a more commonly used dimensionality reduction technique now in single cell. Single cell RNA-seq is by far probably what you're most familiar with in terms of these kind of techniques. This is 100 million cells in the mouse cell atlas. There's the dimensionality of this would be tens of thousands of genes being reduced to 2 dimensions to plot cells and identify patterns. With ChIP-tsne, what we're going to be doing is each region on the genome gets a point in the tsne space, and its position will be based on the similarity in ChIP-seq profiles. So I don't think ChIP-seq needs much introduction. The main point here is that at the end of this process, you end up with enrichment profiles, which are fragment pileups, and then you call peaks on this. And these peaks are your areas of interest in the ChIP-seq experiment. But it's very rare that you would want to look at just a single histone modification, just a single target in a ChIP-seq experiment. You're going to be looking at several at the same time, and you're going to need to be able to reason about these. This is fairly easy to do in like a track view like this, a genome browser type view. But really you need to be thinking about tens of thousands of sites potentially at the same time and in multiple conditions a lot of the time. So other techniques, other visualization techniques for this would be things like Venn diagrams or heat maps. And I want to convince you that ChIP-tsne is a at least interesting way to look at this data. So in order to run tsne, we need a matrix. So what we're going to be doing is for each region on the genome, in this example, there's, say, 3 histone modifications, red, green, and blue. And we're going to be pulling signal from either bigwig files or conducting a BAM pileup. And then we're going to be, we need to identify areas of interest to look at. These would be peaks commonly, or you could also look at transcription start sites or any other genomic features of interest. And the next thing we need to do is bin each of these signal profiles and make measurements. And then we're able to combine them all into a single row on this input matrix for tsne. So this is where the dimensionality comes from. And then you're going to have one row in this matrix for every feature we're looking at. And then we reduce to 2 dimensions with tsne. And you get something like this. Where each point here is represents a region on the genome. This data is for a single K27 acetylation replicate, and I also included the input BAM file as part of the tsne. So this black view is very uninteresting. This isn't what we want. This is just a blob. So the next step to dress up this data is just plot. Maybe a simple thing to do would be to just plot the maximum value in each of these regions for the K27 acetyl in the input. And basically what we're doing here is what I would call peak evaluation. We're just seeing if our peak call worked. We don't see any regions with high input signal. That's great. And we see that same kind of trend I identified earlier, where there's low signal on one end and high signal on the other. But there's also some interesting areas here. So this is the same kind of view that I showed as kind of a teaser. And what this view is really doing is we've divided this tsne space up into 10 bins going across and 10 bins up and down, and we're just averaging the profiles in that space and representing them here. Yeah, we see subtle differences here, I'd say, in peak shape. There's double peaks here. That might be interesting to investigate. And so this is really the starting point of chip tsne analysis. So the experiment I'm going to be describing using chip tsne, we started with this single replicate, but there's a lot more going on here. We're going to have 2 replicates for every condition, so we're concerned about reproducibility. And we're going to have 2 conditions, a control and an induced condition. So this data is in a B-cell leukemia cell line, and this cell line happens to have a mutation in a transcription factor, and we're going to be inducing that transcription factor. We're going to also look at an additional histone modification, a transcription factor, and we're going to even bring in ATAC-seq. So this technique is not limited to ChIP-seq for any particular reason. You can use any of these enrichment-based assays, like ATAC-seq. I've used it on cut and run, and DNA-seq as well. And this data was all generated by Alyssa Richmond and Hanna Pakalova in the Fritz lab. So for replicate comparison, now we're looking at 2 replicates for K27 acetyl, and there's very good agreement between these replicates. There's a little bit of orange poking out on some of these, which is where they're slightly different, but in general, they match quite well. We can bring in other kinds of information to this view. Here we're looking at peak calls. So the green here is the peaks that are shared between the 2 replicates, and then on the end in purple would be peaks that are unique to the replicate 2. There were a lot more peaks called in this replicate, and we can see here that they're kind of biased to this region, which is a lower signal. So we'd have to make a decision, do we want to include these lower signal peaks or maybe disregard them? So differential call evaluation, now we're looking at control and induced. We've combined the 2 replicates. And the input here is actually the merged K27 acetyl peaks, but we've enriched for differential regions. There's a differential call going into this. And this is the exact same view that I've already talked about, so I'm not going to further elaborate. But similar to when we brought in the peak call in the replicate comparison area, we can bring in the differential call. This was done with Seesaw, which is an R package. So we can see the differential call kind of segregates to a large band here for down, a couple blobs here for up, and some other areas as well. And a powerful thing to do here is to combine these 2 visualizations together. So we can see there's a very good matchup between what we saw as differences in profiles, as well as where the differential regions are being called. One thing, if I was analyzing this data, but while analyzing this data, one thing that would pop out to me is that a lot of these differential regions are in the lower signal areas of the genome, and they're less likely to be biologically interesting. So unless there's a compelling reason to preserve them, I might think about going back and filtering my Seesaw differential call. So that was the differential call. Now we're looking at multi-layer epigenomics. We're bringing in these 4 sources of data and looking at control versus induced in both of them. And this is similar to when I was looking at when we were just plotting the maximum signal per region, but here we're subtracting the maximum signal in induction minus the maximum signal in control and generating kind of this differential view of this t-SNE space for these 4 factors. And you can see that, yep, there's a large group of peaks here with different, where K27 acetyle is quite dynamic, but it doesn't really match, like that would be here and here and here. It doesn't really match up with the other modifications that are changing. So what we really want to do is we want to find one area where there's some interesting things going on. So I selected this relatively small area in the middle where ATAC and the transcription factor binding is decreasing with induction, and there's also some faint blue in the K27 acetyl. So zooming in on there and just looking at the summary profiles in that area, we can see the expected differences in the transcription factor as well as the ATAC, and then some subtle differences in the K27 acetyl. Taking these points and putting them into GREAT, which is like a gene set enrichment tool, but you put in regions of the genome, we got a lot of B cell relevant terms coming back. This is really excellent for leukemia. Here's a specific example of one of the regions, so we can kind of take it back to the simple track view that we started at. Quick note about implementation. This is available on GitHub. If you just Google chip t-SNE, it'll show up. And the images that I showed are about 80% directly supported right now. I'm still actively working on this. I used RT-SNE for the t-SNE, and internally there's also 2 other packages that I work on. Involves SeqSetViz is like a tool set for working with next generation sequencing data in a tidy or ggplot friendly way. So thank you all for your attention, and as a special treat, I've included an animated t-SNE plot, which I made when, I don't know, I was having fun analyzing data.
So, thank you, Joseph, for your presentation. Question? Okay. We have time just for one question, please. Very quick.
Sorry. Well, why do you use DSN and no UMAP? Or have you tried? Because there is a difference from the mathematical point of view. At least we see some quite difference in the single cell analysis. Okay.
Yeah, so I haven't gotten around to trying UMAP with this data yet, but it should be relatively simple to just replace inside the function. And I would be interested to see how they're different. In my experience with single cell, just looking at a t-SNE or UMAP, I couldn't tell you which was which in a lot of cases. But you're right, they are quite mathematically different.
Thank you.
Thank you.